Hello. So, we have discussed first the eutectic phase diagram in the last lecture, and we are going to continue the discussion for further details. I told you that there are three different types of eutectic phase diagrams which are normally used in the literature. The first one is this type. First one has very simple one in which we have the two liquidous surfaces coming and meeting at a point on the eutectic temperature line, and that point is given by E here, and on the left side the region which is marked as yellow is consisting of liquid plus pure A. Pure A is the component. On the right side the green region consisting of liquid plus pure B, but B is the second component. And below the eutectic temperature, which is given as TE, that you have only A plus B as a solid. So that means the eutectic reaction is given by liquid going to A plus B. This is the first type of phase diagram which we have discussed. Second type of phase diagram is like this, like a lead and tin, in which we have the eutectic reaction at the temperature of eutectic temperature of 183 degrees Celsius here for the lead tin system, but also we have two ends. The two ends means the ends of these two components are not as pure, but solutions of lead, and in which tin is present on the left side. On the right side you have solution of tin in which lead is present. So that means these are the two are called terminal solutions in the literature. Terminal is because they are the ends of the two components, that is why they are called terminal solutions. And because of the presence of these two terminal solutions, the eutectic reaction is little bit modified. Liquid goes to lead solution plus tin solutions, and this is the second type of phase diagram. Third type of phase diagram, which we will discuss within the later part, is known as the for the aluminum silicon system, which we will discuss later. Now let us move and show you. I will show you first some typical microstructure of the eutectic systems. Then we will discuss how these microstructures actually form, because as you understand, eutectic phase diagrams has the reaction given by liquid going to two solid phases. So because of this simultaneous formation of two solid phases from the liquid, there are different types of microstructures which can form during solidification. So therefore we have many choices, or many rather not choices, many different types of microstructure possible. So for the I will start with for the classical lead tin example, because lead tin is used as solder material still now for all the electronic gadgets. So because of that, lead tin is a classic system, and the first microstructure which is showed here is a lamellar type for the lead tin eutectic system. You can see here that you have a white or a grey, rather grey and black lamellae, I could say. Please remember this term lamella or lamellae. Lamella is basically a singular in English, and lamellae is a plural in English. Lamellae means many, and lamella means one. So you could see here that these grey regions, I can point out here, grey regions there are basically the tin. Okay. On the other hand, the black ones are basically lead, but they are in a lamellar morphology. What is the meaning of lamellar? Okay, means they are slabs. They are actually slabs sitting on each other like this, one above the other. So thin dimensionally they are slabs, and when we cut and see under optical or microscope or scanning electron microscope, we see two dimensional section, and there it looks like a line or like a curve. So here you can see continuously, you can see the curves going from one end to other end, and this is the classical microstructure of eutectic. So whenever you see such a kind of microstructural features in any sample while examining, suppose in your lab by using optical microscope or SEM, we tell this is due to eutectic reaction, where the eutectic reaction is given by liquid going to lead solution plus tin solution. Here tin is in beta phase. So now one can actually simulate this microstructure in using computer simulations, and you can see here 3 dimensionally they look like a slab. So, this is the green ridge slab, the blue slab, this is the yellow slab, sorry, this is the blue slab, this is the yellow slab. You can clearly see they are actually looking like a long slabs in 3 dimension, and when you cut it you see a 2 dimensional section, they look like a lamella. Now, let us look at another system which is little bit of complex, but do not bother now about reading the phase diagrams, because the course is basically is meant for phase diagrams. So, right now we only look at the relevant parts of the phase diagram. You see this is a phase diagram between niobium and silicon, but we are only showing only half of the phase diagram now, where silicon concentration varies from 0 to 50, other 50% or 50 to 100% I am not showing it. So, reason is very simple, there is a eutectic reaction marked by this red arrow, you can see it is written eutectic. This reaction takes place at very high temperature 1880 degree Celsius, and at by the reaction we form 2 solids as usual. One is niobium solute solution, NB solute solution. I said you solute solutions in a phase diagram are marked by these first brackets. So, the moment you put first bracket around NB, that means that is a solute solution between niobium and silicon, or rather that means silicon is inside niobium in the same crystal structure of niobium, that is why it is called niobium solute solution. Just like a liquid solute solutions, but it is in solid state. In liquid solutions you suppose take water, add sugar. So, water is a solvent and sugar is the solute. Similarly, here a solid solution, niobium is a solvent, silicon is a solute. Why niobium silicon is a solute? Because silicon percentage is very small, maximum is about 3.5%. So, this reaction will produce niobium solute solution plus Nb3Si. Nb3Si is an intermetallic phase. We will discuss that in our subsequent lectures. Intermetallic phase. Why it is called intermetallic phase? Because it has 2 metals, or rather it has 1 metal and 1 metalloid, but anyway it does not matter. Nb3 plus Si, it has a fixed stoichiometric composition. So, eutectic reaction will give into these 2 phases together. What kind of microstructure will produce? Forget about other parts of the phase diagram, do not concentrate even right now. So, this will produce such a kind of microstructure. You see here they looks like a rod, okay, exactly look like a rod. At the pen I show you this exactly look, this is like a rod. So, they look like a 3 dimensional rod and they are arranged in a very peculiar fashion. Some of the cases they are arranged like a hexagonal manner. So, there is a arrangement possible, and such a kind of thing happens because of certain reasons. So, we have seen lamellar microstructure, lead tin, this is rod type of eutectic. So, why such a kind of change happens we will discuss later, but first you observe that there are variety of microstructure possible in a eutectic system. Now, you can always simulate this microstructure and you can see that these rods are possible to see in the microstructure. There is another type of microstructure known as globular eutectic. What is that? It is normally found between Cu and Cu2O. If you have a copper melt and if you have sufficient amount of oxygen present during solidification, then such a kind of things forms. Here Cu is basically looking like a continuous grey color stuff, you see here grey color stuff continuous, but these black dots are actually globules of Cu2O. You can see they are formed as a grain structure, okay, I have shown you earlier. This is a grain of one grain, this is another grain, this is another grain, like that. So, they are actually looking like a globule, not like a rod, they are looking like a globule. Okay. Difference between globule and rod is that rod is a continuous long object, globule is a simple small object, it is like a one round separate object. So, that is what is the globule. So, this is globular eutectic. Another interesting type of eutectic forms in spiral, that is found in magnesium zinc system, and this eutectic is between magnesium solute solution and MgZn2 phase. You can see here they are like a spiral, very fascinating microstructure. One phase is spiraling continuously. Why does it happen? It is basically very not difficult to understand, is I will explain in detail. If you have 2 phases going side by side suppose, and their thermal expansion coefficients are quite a lot different. So, the moment you cool it down from high temperature to low temperature, then only you can form this microstructure by eutectic reaction. So, the moment you cool it down from high temperature, the thermal, because of thermal contraction, the contraction of those two phases will be different because alpha or thermal expansion coefficient is different. So, because of that they bend, one guy will bend. This is like a bimetallic strip. If you hit a bimetallic strip, the one which is higher thermal expansion coefficient will expand faster than the other, and then the whole thing will bend. This is exactly happen here. So, once you cool it down, one guy is basically shortening faster than the other guy because of the different thermal expansion coefficient, and this leads to spiral formation. Those who have done engineering mechanics course, they know that this is how the spiral is done. You can see here one spiral there, other one there, another one there. There are many, and each of them actually forms a grain. This is the beauty of these eutectic systems. You can connect different type of microstructures. Yeah. So, now I discuss the third type of eutectic system first, then I will discuss the microstructure. The first type of eutectic system I showed you, there is no terminal solution. Second one I showed for lead tin, there are two terminal solutions, and third one I showed you, I will show you for aluminum silicon system. See, this is the phase diagram of aluminum silicon system, and this is the pure aluminum end, this is the pure silicon end. Silicon concentration varying from 0 to 1, this is fraction, that is why 0 to 1. So, that means 0% to 100%. Eutectic reaction is here shown by a red arrow, and you see eutectic is between alpha aluminum and silicon, pure silicon. So, that means there is a solid solution field here at the aluminum end, but there is no solid solution field in the silicon end. Silicon remains pure, it does not have, aluminum cannot get into silicon to form a solid solution here on the silicon end, but silicon can easily get inside aluminum and form a solid solution, and that is known as alpha aluminum, because aluminum has FCC structure. So, that is why it is called alpha. Alpha is the first Greek letter. So, phase diagram starts with that. So, that is why alpha aluminum, or you can write them aluminum within first brackets, then it is also a solid solution. So, you can clearly see there is a eutectic reaction here. So, this is third type where there is only one end has solid solution, other end does not have anything. What kind of microstructure form? Okay, let us first tell you, this is a very important alloy system for all car engines. All the car engine blocks which actually uses aluminum alloys contains this aluminum silicon, because aluminum silicon is a very easy to cast and high strength aluminum alloy, that is why it is easy used. What is the microstructure? Okay, it is very different from all the others you have seen. You see here black and white, grey color things, grey color thing is which is continuous is aluminum, alpha aluminum or aluminum solid solution, whatever you define, and these black things what you see here long needle like structure is basically silicon. They are fibers actually, they are like asbestos fiber exactly, and they grow in this way different kinds of directions, and you know silicon is a metalloid, that is the problem, that is why growth of silicon has problems, and there are many issues, many research is going on in the world. I am not going to discuss how to do that. Aluminum silicon is a very interesting alloy system. Okay. Now I also go back to the phase diagram. I told you eutectic composition is given by this red arrow. The any composition below this or less than that is called hypo-eutectic, above is called hyper-eutectic. Remember, hyper-eutectic alloys will contain silicon as a primary phase, which I will discuss and tell you why. Hypo one will contain primary aluminum. So, hyper ones will have, because primary aluminum is ductile, on the other hand primary silicon is very brittle. You can take a silicon piece and just put it like this and drop, it will break into, shatter into pieces. Silicon is so brittle, but aluminum is very ductile. That is why hypo-eutectic aluminum silicon alloys are used extensively in the engine blocks or aluminum in the cars. So, you will have this aluminum dendrites, and in between you will have eutectic. You can clearly see aluminum dendrites and this. A dendrite means tree like structure. It is there like a tree. Tree has a trunk, you can see this is one trunk, another secondary trunks, you have tertiary trunks also possible. So, and then you have eutectic in between. So, I will again come back. On the other hand, hyper-eutectic alloy you will have silicon, no dendrites, silicon as a piece. You can see here silicon, faceted silicon crystals around and eutectic, and these silicon crystals are brittle. That is why hyper-eutectic aluminum silicon alloys are rarely used in the applications. Another classic example of eutectic alloy is iron carbon or rather cast iron. All of you who are in the industry, they know the cast iron is the most important material for automobile industries. It has lion shares in the automobile industry. So cast iron has a eutectic phase diagram, and eutectic is between gamma iron and carbon or graphite. So you can see here, this is the graphite nodules, they are like a nodule, okay. Nodule means the C nodule like picture, and you have gamma iron around it, okay. You can clearly see that, and these things you see here is a transform product of gamma iron to pearlite. Let us not bother right now, this is not due to eutectic reaction, but this is due to eutectoid reaction, which we will discuss in detail manner when we discuss eutectoid. So eutectic reaction is between liquid going to gamma iron plus graphite, and graphite comes as a nodule, gamma iron is looking like a white thing, okay. Now there is another eutectic, which is cobalt copper eutectic. You see here also the carbon cobalt carbon eutectic, carbon is coming as a graphite needles here, and cobalt is a continuous grey matrix. So I have written graphite needles in a cobalt matrix, very important material because of strength, okay. Then you have many others, I do not want to talk about much. So in a nutshell, these are the 4 different eutectics I am showing you together. One is indium tin globular eutectic, aluminum silicon known as acicular fibrous eutectic, you can see here I have discussed, and then this is lamellar, again aluminum copper, lead tin also lamellar, and there is another type between magnesium tin, Chinese script type. Chinese scripts are very difficult to understand, they look like a tree, look like many things. So any kind of structure which forms like that kind of is called Chinese script microstructure. This is well documented in literature, correct. So I will not go back into phase diagram, so let me just now discuss what happens for hyper and hypo-eutectic. Let me just go back, okay, yes. So I told you that in the last class I am going to discuss 3 alloys solidification and tell you what actually happens. So let me first tell you that there are 3 alloys, means one is eutectic alloy, other one is a hypo-eutectic alloy, and third one is a hyper-eutectic alloy for a phase diagram which is looks like a most common one where we have 2 turbulent solution like a lead tin one. So let us now go back to board and discuss that. So I will first draw this phase diagram which looks like this. Let me just make it bigger. Between component A and B, I am not using any name of elements, only component A and B. And one thing I want to stress upon that, you must know this is the way to be done, A and B XP, please do not forget that whenever you draw a diagram. Now I draw the phase diagram, this is looks like this is the primary phase field of A solution, this is the on the B side, and this is the eutectic reaction, okay. So this is alpha. I told you that any phase diagram will start with the first Greek alphabet alpha, then you go on beta, gamma, delta. So this is also beta, and eutectic reaction is liquid going to alpha plus beta, which is happening at this temperature T at this composition Ce. So this is alpha plus beta, and obviously between these two it will be alpha plus liquid, between these two it will be liquid plus beta, very simple. So I am going to discuss with you this alloy first. I put a dotted line, and then this one I put another different kind of dotted line. This is hypo, and this one I put it like this way, hyper. So this I term hypo-eutectic alloy, this I term as a hyper-eutectic alloy, and this as a term as a this one as a term as a eutectic alloy. So it is better to start with the eutectic alloy. You know, like a lead tin picture I shown you. If I start with a eutectic alloy system here, and what will happen? I cool it down completely, liquid will remain present even above the eutectic temperature T, because you can see here this is completely liquid field. So liquid will remain. Only below the eutectic temperature liquid will react and form two solid phases simultaneously. How does it come? Okay. So, let us consider this picture. I draw, this is a temperature above the eutectic temperature T. I have a completely liquid in the sample because I am above the eutectic temperature. Okay, nothing has happened. It is a liquid. Correct. So now I just drop the temperature just slightly below the eutectic temperature. What will happen? If I drop the temperature slightly below the temperature, it provides a driving force for formation of the solid phase because you are below the eutectic temperature, and that means nucleation of both the solid phases are possible, alpha and beta. Let us suppose alpha nucleates in one of the things, alpha nucleates, okay, here like a dot, and this is my alpha. Beta can also nucleate, does not matter, I will tell you why. But suppose for the understanding, let us say for the suppose understanding that alpha nucleates. So as you see here, alpha is rich in A, but very poor content of B. Can you see here? Alpha is near the A end, this is pure A, but it contains very little amount of B. So if it has to grow into the liquid, suppose it grows into the liquid like this, it will reject all B because it needs A. To grow it needs more A, less B. So it will reject all B into the liquid. So B will come out in front of the alpha as it becomes bigger. As it becomes bigger and bigger, it will reject B. So if it rejects B, what will happen? The regions nearby in front and also side will have B, lot of B, plenty of B. B is the second component, plenty of B will present, and because of that these two places, because there are large content of B and beta contains huge amount of B, very large content of B, because beta remains in the B end or rather near the pure B. So beta has more B, less A. So because of that, if the concentration of B increases on the both sides, beta will nucleate after certain time, and beta will form like a, again grow like this. So as you see on the both side of alpha, I have drawn two lamellae of beta, correct. So as you know, for growth of beta you need more B, growth of beta, growth of this is beta. So for growth of B you need more B. So if you need more B, that means what? All the A will be rejected in front of by beta, all A will come out, okay, this is small, all A will come out in front of beta or side of beta. As the A come out, A will be concentrating here more, and as the A concentration will increase, then alpha is, then when the A will be very large content on both sides, it is easy for the alpha to nucleate and grow on both sides. So like that way again beta will form, and that is the way you form a lamella, okay. This is the way you will form a lamella structure. You can see here lamella structure, same way what you see for Latin. Similarly here one other lamellae will form, alpha beta, okay, this will grow. Similarly another one there, another one there, another one there. So then each one will merge and form the whole microstructure. Okay, now suppose I told you beta nucleates, suppose instead of alpha here beta nucleates and grow. If beta nucleates and grow, it will require more B, because it requires more B it will reject A in front of it and also in sides of it, and because of the A concentration increase on both sides in front of it, that will lead to very easy nucleation of alpha, because alpha is rich in A. So as the A rejected more into the liquid on the both sides, A concentration will increase around it, and A concentration will reach very high value, alpha which contains most of A will nucleate and grow like this. And when as A grows, as alpha grows, this is beta and this is alpha, as alpha grows it will reject B, because alpha is basically pure A, almost like a pure A, very little amount of B is present, alpha is a rich solution. So because of that B will be rejected. As the B rejected, B constants will increase on the both sides, and this will lead to formation of beta, and so on. So it does not matter whether you nucleate alpha or beta at the beginning. What matters most is that you form a lamellar structure. So this is what will happen in all the cases. Okay, I am not drawing it, but this is what will happen in all the cases, all the one. Okay. Alpha beta, beta alpha, like that, and you form the whole microstructure. Okay, so in the next class I will discuss about these two hypo and hyper-eutectic cases. Let us finish this one, we will discuss about the next class.